Okay, so we have our golfing data here, and we have 4 observations for each combination of driver and club. Now, in SPSS, in clubbrand.sav, you can see here that we have exactly the same information in kind of long format. So we've got driver, brand A, 4 observations. 5-iron, brand A, 4 observations. Driver B, 5-iron B, C, and D. Now let's go to Analyze, General Linear Model, Univariate, as before. Now, a dependent variable, as always, is the distance, and our factors are club and brand, are our fixed factors. And what we want to do is we want to click on the model button, and we just keep the full factorial design. The full factorial design basically means we have each of the factors and any interactions between the factors. The sum of squares, now this, we're only going to do balanced designs. The balanced design is the design where you have the same number of replications in each cell. And for that, all these different sum of squares are the same value. But if you have kind of missing observations or uneven observations, then different types of sum of squares do different values. For this class, we're just going to stick at type 3. Now we're also going to have some interaction plots. So let's just say that we're going to have club on the horizontal axis and brand on the separate lines, just like I drew in the previous video. One factor on the x, one factor on separate lines, and the dependent variable is on the y. Now let's just do the opposite. We get brand times club. And post hoc, yeah, let's just assume we're not really going to focus on this, but let's just have some Bonferroni post hoc tests, the club and the brand. And I think that's pretty much it. So we have an overall ANOVA table, and we see that pretty much everything is significant. Now we could actually just quickly, let me just get a snippet of this. So let's go full screen snip. Get rid of our old one. Let's get that, and let's zoom in a little bit. And let's just have a few annotations. So you can see here the degrees of freedom. This line here is the overall model. See, we have the 8 means. Oops. So this is AB minus 1. We have 8 means, 7 degrees of freedom, and this is the sum of squares for the overall test. And you can still see the mean squared here divided by the error. Is the F statistic for the overall model. Then we have these 3 separate tests. Remember, in this instance, the club is factor A, the brand is factor B. This is the row for the interaction of A and B. So all these are kind of the numerator rows. And then we have the denominator row, which is going to be the error. Yeah, I'm not very good at drawing these. Let's choose a different color. Let's just go with green. So you can see this is A is 2. We have 2 clubs, so this is A minus 1. We have 4 brands, so 3 is B minus 1. And this is A minus 1 times B minus 1, i.e. 2 minus 1 is 1, and 4 minus 1 is 3, so that's 1 times 3. This is 2 minus 1 is 1, 4 minus 1 is 3, and then the error degrees of freedom is going to be AB R minus 1. It's going to be 2 times 4. We've got 4 replications times 3 is 24. This all matches the ANOVA table that we did before. Okay, and I've drawn too much over this, so I'm actually going to do another one now, which will utilize, let's just make it a little bit bigger, not that big, which we'll utilize when we go over the tests. Okay, so the tests I'm not going to actually write out. I'm just going to kind of give a little bit of insight into the tests. And I'll kind of annotate some of these with my pen. Okay, so this is the overall kind of the omnibus hypothesis, which is basically, you can see here, this kind of clue here is, let me just change my pen color. Across the 4 brands and 2 club types. So we're looking at basically all 8 kind of treatments. And you can see here, this is at the beginning, we've got 1 and 2. These are the levels for the club. And the 1, 2, 3, 4 are the levels for the brand. I could actually give these names if you wanted. So we could have mu 5 iron, comma A, mu 5 iron, comma B, mu 5 iron, comma C, mu 5 iron, comma D, mu driver, comma A, mu driver, comma B, mu driver, comma C, etc. Or this is actually a bit cleaner, just giving the numbers. Or we could just say something like no difference between among the 8 treatment means. And for ANOVA, apart from the interaction test, the HA is always the same. At least 2 treatment means differ. So the test statistic is the mean squared treatment over the mean squared error. Remember, this is just really, we're just doing a completely randomized design on the kind of omnibus test on these 8 means. Okay. So we've got the V1 is basically going to be the AB minus 1. So that's the number of means, 8 minus 1. And remember, this is the equivalent to the completely randomized design. These were like K's. So it's like we have K, we've got 8 means, and the number of means here is A times B, so it's 8 minus 1 and minus 8. So we have 7 degrees of freedom and 24 degrees of freedom. I'm not going to, at this stage, I think you can see how to look at the F charts. We did them before, but you go along to 7 and 24, 0.05. Actually, let's just validate this. Yeah, we'll keep that. Let's just kind of look at that. But we have 7 and 24 across is 2.42. So there we go, 2.423. I guess I got that from Excel. And the F is the mean squared treatment over the mean squared error. So let's just look at this. Let's just look at my SPSS output. Let's just, here we go. So in this case, it is, let's just draw a circle. It's this figure here, which is the mean squared divided by the error. And of course, SPSS, we could reject significances left, p-values less than 0.01, because I mean, it is a whopping big F value. It's way, way beyond the edge. So we also say, oh, I can't believe, yeah, there we go. We'd also say that P is less than 0.001. I think this is actually probably the best way of doing it if we're going to keep jumping backwards and forward as SPSS. So anyway, we now have the club's hypothesis, which is factor A. So this is the across the two, does the mean difference differ across the two club types? This is the mu1 equals mu2, or we could also write mu 5 iron equals mu driver, and standard alternative hypothesis. The test statistic is the mean squared A over the mean squared error. And again, going back to the ANOVA tables we've done a few times, the V1 is the A minus 1, 2 minus 1, 1 degrees of freedom, and the V2 is the error, which is ABR minus 1, or N minus AB is exactly the equivalent, which is A is 2, B is 4, R minus 1 is 4 minus 1. So that's going to be equal to 24. And we actually have 1 degree of freedom and 24. So let's just do 1 all the way down to 24, and we have 4.26. There we go. And let's just go back to SPSS. Okay, the cut version of SPSS. So for the club, mean squared, same error as before, 32,000 divided by 34 gives us this F, 936, which is way, 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 way bigger than 4.26 for obvious reasons. P is less than 0.01 or 0.01 in all of these cases. So it's very low. It's going to be less than the alpha as well. So that's another way of rejecting it. Here, you know, massive F. F is greater than 4.26. So reject H0. I guess I just there were so many tests here. I got a bit lazy and didn't write the actual final thing. Okay, so we now have for the brands. So this is factor B across the 4 brands. So we've got mu A equals mu B equals mu C equals mu D is equivalent there. Or you could just say, you know, the levels for, there's no difference among the levels for factor B. Okay, we can look at this, and again, the V1 is, from the ANOVA table, is B minus 1, 4 minus 1 is 3. The error degrees of freedom does not change. 324, so we go across 3 on the numerator, 24 on the denominator, and we have 3.01 or 3.008. I guess, again, I was doing from Excel. And the F statistic is going to be this one, divided by the error, 7.7791. Again, P is less than 0.01. So we can write F equals 7.791, which is greater than 3.008. So reject H0. And the P, you know, looking at SPSS, we have P is less than 0.01, which is obviously less than 0.05. So again, reject H0. Okay, now just if you were falling asleep in the rest of the video, don't wake up now, because this is the interactions. So this is the interaction between A and B. And even PhD students start trying to write out means here, and it's just simply factors A and B do not interact is the null hypothesis. Factors A and B do interact is the alternative hypothesis. You could put the brands, you could put like, brand and club type and brand instead here. So you could do club type and brand, but whatever you do, don't start writing out means in an interaction, because I will knock points off on an exam for that. So it's the test statistic is the mean squared AB. And again, exactly the same, but A minus 1, B minus times B minus 1 was the numerator degrees of freedom, which we did before was 1 times 3 is 3. Denominator doesn't change, so it's still 324, so it's the same as the one for factor B, so it's the same F value. And the F statistic, yep, get the one, so it's club times brand over 34, 255 over 34 is 7, which is our final thing. And you can see, oh, this p-value is around 0.01. So it's actually still less than 0.05 according to SPSS. So F equals 7.452 is greater than 3.008. So reject H0. And from SPSS, we have the P is approximately equal to 0.001, which again is less than our alpha, so we could reject H0. Okay, last little thing is the effect size. We'll talk a little bit about effect sizes. And I'll just let you kind of play around with these a little bit. So we just got to do the effect sizes and also look at some of the Bonferroni on this. Now, there's some of the experiments I do, you've got like, so I do algorithm design. So let's just think about mine. I do algorithm design. And I might have two factors. I might have A is the data set, and B is the algorithm. And I'm doing an algorithm to try and perform better on a certain data set. But usually the error is really dependent on the data set. Most of the error is dependent on the data set. So this is huge compared to this, which is the one I'm interested in, which is smaller. So it looks like I have, if I was to do basically SSA all over SS total, then this would be large. But SSB all over SS total would be very small, even though relatively, I know there's going to be a huge effect for data set, but it doesn't really bother me. I just want to know there's a difference between the algorithms. So it really just kind of lowers my effective effect size. So in this case, I'd use a partial eta squared. And this is basically just the factor divided by the factor plus the sum of squared error. So it's just sum of squared factor. It's just saying how much, how large you are relative to the error variance, which is the point of ANOVA. So if my factor is really large compared to the error, I have a high partial eta squared. Of course, this is going to go between 0 and 1. It can never get bigger than 1 because with no error, then we get a perfect 1. If we have no factor and, it's all error, then we get a partial eta squared of 0. And as usual, we have something we can calculate from a paper if we're doing a meta-analysis. So we have partial eta squares. It's the degrees of freedom for the factor times by the F for the factor. So let's just kind of, I won't work it out, but just show you what it is. So say for factor A, we've got, say for club, we have a degrees of freedom of 1 times 936.752. All over this, plus the degrees of freedom for the error, which was 24. So you can see this is very close to 1. And we're going to actually calculate it in a second. And our final one is the partial omega squared. And this is kind of just, again, we're kind of removing the bias for taking a sample, and we're trying to estimate the population value. And this is the sum of squares factor minus the degrees of freedom factor times the mean squared error, all over the sum of squared factor plus n minus degrees of freedom factor times the mean squared error. And again, to derive these things from scratch would take a lot of time and a little bit beyond, of course. So let's just have a look at the golf example. Now, again, most of the variation here it's almost a little bit like my algorithm example. Most of the variation is in the club, and it's obvious, you know, if you play golf, a 5-iron and a driver are designed to hit the ball different distances. So this is going to take the lion's share of the variation. So we see the sum of squares for the brand is 800. And remember, we're using the corrected total. The total sum of squares is going to be 34,482.049. So let's just kind of have a look at this here. It's 0.0232. So this is kind of the n squared. This is low, as most of the variation is in the club. But relative to the error, you know, we have about the same variation as the error. You see the error has 822.2 and the brand has 800. So you can see that this is much higher. So this is just to the error is much higher. So here's the omega squared. So again, very similar. We've got the 800.736, 800.736. But rather than just dividing by the error, we're kind of adjusting for sample bias. So here we subtract degrees of freedom of the factor, which is 3 for brand, times the mean squared error. Let's just go here. So the mean squared error is 34.26. And plus n, we have our total n is 32, minus the degrees of freedom factor times the mean squared error. And that's 0.389. So again, we're not deriving the formula, but generally this is a little lower. So let's actually, for fun, let's just do the n squared partial for the club, which is going to be very large, as we said, most of the variation is in the club. So let's just have a look. The error of 822 is going to be the same. So the variation of the club is 32,093. From 11 all over 32,093.11 plus 822.24. And that gives us, let's just look at the calculator. So we have 32,093.11 all over. So it's 0.975. So a huge amount of variation in the experiment is due to the difference between clubs, which is to be expected. You know, a 5-iron and a driver shoot completely different distances. So it's kind of got a real world application there. Okay, last little thing, effect sizes. Now notice we only have effect sizes for the brand. We don't have it for the club. But then it's kind of pretty obvious with I could have just done a club chart, but it's pretty obvious here from this chart that the driver goes much further than the 5-iron. And essentially, you know, this F test for club with one degree of freedom, 2 means, you get the results is essentially the same as doing a T test. So let's have a quick look at brand. And let's just do what we did when we did the ANOVA, the single factor ANOVA, and the multiple comparisons. So let's just kind of start off at the bottom. Which one has got basically everything positive, which is brand B. And you see that the mean difference between brand B and A, C, and D is positive, which means that B is going to be less than the 3 other brands. Now, if we kind of look at this, the only one where it's significantly different is between B and D. We've got kind of a difference of 3 to C and a difference of 8 to A. And none of those are actually significant here. If we look at this, because B and A goes through 0, C and B goes through 0, but D, which is the biggest difference, that actually is significant. So I could actually draw a line here between B, C, and A because there's no significant difference. Now look at C. No significant difference between A, no significant difference between B, but there is a significant difference between C and D. Now let's look at A, and A doesn't have a significant difference between pretty much any of these. So we look between A and B, the 0 is in the confidence interval, A and C, 0 is in the confidence interval, A and D, 0 is in the confidence interval. So we can actually draw a line between A and D. But we don't draw one line across because D is significantly different from B, C, and A. Last thing I'm going to show you, I promise, is just this interaction chart. And you can see a little bit, you can see the lines cross, they're not completely parallel here. So you see that brand B is the highest for 5-iron, but it's less than C for driver. And you can see this kind of crossing here that C is the 3rd highest for 5-iron, but it's by quite a bit the highest for the driver. Okay, so we went through all the tests. We did a bit on the effect sizes. Then we went back to our how to interpret the multiple comparisons in SPSS, what we did the previous week of drawing the lines across. And I had a quick look at some of the charts. Okay, that's it.